be on the exam. Remember, you have an exam on Thursday. It's going to cover everything up to 3.4. All right. And then we'll finish 3.5 tomorrow, but it will not be on the exam. All right. Okay. So here we go. So we talked about, right? What did we do yesterday? Hopefully you remember. We did stuff like saying, we talked about adding functions together. And we said, oh, that's just the function plus the other function. And that's how we wrote it, f plus g of x, to get a new function. All right. We did some other stuff. We did subtraction, multiplication, division, right? Remember, multiplication was like this. And that was just f of x times g of x. All right. No. There's no sinking yesterday. And if it was sinking, it wasn't sinking like dying. It was sinking like, imagine taking a bath, but the whole bath is like Jello, but not like the sticky, gross Jello, but like soapy Jello. So it's like it cleanses you, and you sink into the soapy Jello, and it's nice and relaxing. That's what happened yesterday. Perfect metaphor. And we talked about some other stuff. We also talked about the big ticket item was function composition. Wait, that was not a pretty picture? Gross? What? I'm disappointed. Soapy Jello sounds fantastic. I've never bathed in Jello either, Gabe, but I'm sure it's, I don't know. This one was the big one, right? And this was f of g of x. And we started on the inside, we worked our way outside. We evaluated g, and then we simplify it from there. All right. So today we're going to talk about the dreaded words, domain and range. Again, how can we find the domain and range of function composition? Okay. So here we go. To find, actually, we're not going to talk about range. I lied. I'm a fibber. To find the domain, remember, domain is all the inputs, all the things that you can plug in of f of g. And remember, sometimes we write f of g of x. Sometimes we just write f of g. For the purposes of this class, they're basically the same. You don't really need to know the fine details of when they're different. To find the domain of f of g, this is kind of complicated. First, find the domain of g, the inside function, and see what it has in common. That's not how you spell that word. Let's fit another one in there. See what it has in common with the domain of f of g. All right. And this is a really confusing way to put it. There's a ton of ways to say this, but really the best way is just to do it, okay? So we're on example, I don't remember what example we're on. We'll call it 77. I'm sure we have not done example 77 yet. So we're just going to make this example 77. And maybe we skipped a few, but we haven't done this one yet, okay? Find the domain. Example 7. Oh, I was close. Great. Find the domain. Thanks, Monet. Of f of g. In part A, where f of x is equal to 5 over x minus 1, and g of x equals 4 over 3x minus 2. So this problem, this is going to be a big ticket problem, okay? This problem is going to be, I won't say juicy because apparently that makes you uncomfortable. This problem is really slimy, okay? It's got a lot of slime to it, all right? It's going to get everywhere, and you're going to have to be really careful, okay? Wait, is slimy even worse? All right. Slimy, we'll add that to the list of things that I'm not allowed to say, okay? It's a good problem, okay? So, right, first we need to find the domain of the inside function. So let's see, f of g of x, remember, is just f of g of x. Oh, I found the inside function. Inside function's right here. It's g on the inside. No, Gabe, while you were gone, I was also informed that moist is an inappropriate and unsuitable adjective to describe a math problem. So sorry about that. Okay, so what's the inside function? The inside function is g of x. G of x is 4 divided by 3x minus 2. So we just plug that in. We replace the g of x with what it equals, 4 over 3x minus 2. And as soon as we do that, as soon as we're looking at the inside function, we need to ask ourselves, what's the domain of that inside function? Because remember, to find the domain of the function composition, we need to find the domain of the inside function and find what it has in common with the domain of the final function. Okay, so this is the first thing we have to look at, right? Let's call it like D1. How do we find the domain of this inside function? What is the domain of the inside function? What's something we know about the domain of the inside function? Someone let me know. Four over 3x minus 2 is the inside function, yeah? But how do we find the domain of that function? Just the domain of this thing right here. Talked about it a little bit yesterday, where if we have a fraction, we can't divide by 0. So we're not going to multiply it by anything. We need the denominator to not be 0. Just like if we want a real number and we have a square root, we need the inside of the square root to be positive or 0. So for the first domain, we need the denominator not equal to 0. So what we need is we need 3x minus 2 not equal to 0, because 3x minus 2 is, is the denominator. We cannot divide by 0. We divide by 0, bad things happen, okay? Would cause the end of the universe, where it'll cause, like, I don't know, some kind of viral pandemic or something. We don't want to do that, okay? The world's dealing with enough without you dividing by 0, okay? So what's the restriction here? 3x minus 2 can't equal 0. Add 2 to both sides. 3x is not equal to 2. Divide by 3. X can't be 2/3. Right? Lexi, it may very well have been what the cause. Who knows? So to make sure not to do it. We don't need another virus. All right? Okay, so that's our first domain. That's our first restriction. Because remember, we have to find whatever's going on with the inside function and whatever's going on in the final function. So we've got half of it. Well, to find the domain of the final function, we have to find the final function. Okay? So we got to keep on going. And this is where things get really interesting. Interesting is maybe not the right word. Okay? Remember, we are plugging this into our f function. We are plugging this inside into this function. So what is f of x? F of x is 5 divided by x minus 1. So we have 5 divided by x minus 1, but instead of an x, it's becoming this whole thing. Everywhere that there's an x in the function, we put in this inside, which is 4 over 3x minus 2. And hot diggity, look what we've got here. We've got ourselves a bona fide complex fraction. Doesn't this look like fun to simplify? Okay. So You go back earlier in the semester, you say, have we talked about complex fractions before? Have we seen something like this before? And indeed, we have. This was in Math 930, beginning of semester. We said 2 ways of dealing with this, writing it as division or multiplying by the LCD. Okay? So we have to multiply the top and the bottom by the LCD. So your algebra skills, if they got rusty, now's the time to de-rust. All right? Algebra never goes away. Well, that's arguably true. In a math class, algebra never goes away. So as long as you're taking math classes, you're just going to always remember the beginning of spring 2020, our time together with algebra. Okay? How did I get on 5 on the top? Oh, yeah. So that does look kind of confusing. So the 5 has actually nothing to do with this. The 5 is because we are looking at f, the function f, and the function f is 5 divided by the input minus 1. So that's what we have here. We have 5 divided by the input minus 1, but this time our input is not an x. Our input is this whole inside fraction. So it's 5 divided by that input minus 1. Okay. Good question. Thank you, Gabe. So let's multiply the top and the bottom by the LCD. The LCD is 3x minus 2. And once we do this, we will get rid of the complex fraction. So on the top, we can either keep it factored or distribute it. Usually we want to keep things factored on the top. For now anyway, 5 times 3x minus 2. Yeah, I'm smart. Runs in the familia. And on the bottom, you have to be very careful. We have to distribute it. We have to multiply it by this 1 and multiply it by this fraction. But notice what happens when we multiply it by the first fraction. We've got a 3x minus 2 on the top and the 3x minus 2 on the bottom. When we multiply it on the first fraction, they cancel. So the whole first fraction just becomes a 4 because this cancels with the denominator. And then over here we have 1 times 3x minus 2 when we distribute it to the 1. Okay? Distributing it twice on the bottom, multiplying here, they cancel, we just have the 4. Multiplying right here is just the 1 times the 3x minus 2. Okay? So things are getting better. Not quickly, but they are getting better. Okay? And again, there's no cancellation that can be done right here because we have that subtraction sign. We need to combine like terms. Okay? How do we combine like terms? Keep the top the same. And the bottom, we distribute that negative 1. We got 4 minus a 3x plus a 2. And we just keep combining. All right? So what does this become? This becomes 5 times 3x minus 2. 4 plus 2 is 6. So you get 6 minus 3x. And a lot of times when we're dealing with rational expressions, a lot of times when we deal with rational expressions, the best thing to do is leave everything factored. So we're going to keep the top factored and then we're going to factor the bottom. But we only factor the bottom after we've combined all the like terms. Why does this one cancel? I can show it off over here. If this is your question, if it's not, please interrupt. So when you distributed it on the denominator over here, right? So the top is fine, right? 5 times 3x minus 2. But when we distribute to the bottom, what is this multiplication? This multiplication gives us 4 times 3x minus 2. And we were still dividing by a 3x minus 2. And we had the 1 times the 3x minus 2 as well. Okay, so this numerator is the same we had over here. This minus 1 is the same as we had over here. The question is specifically about this term right here. Because notice what we're doing. We're multiplying a non-fraction by a fraction. So we think about this as divided by 1. So it only multiplies into the top, and the bottom gets multiplied by the 1. Right? And then they canceled right here. So that's how they multiplied, and that's how they canceled. Thanks for asking. It sounds like it answered your question, but if not, let me know. So we're going to leave our final answer in factored. I really want to fit all this in one page. Forgive me. So we factor the bottom. Greatest common factor is a 3. And we're left 2 minus x. And nothing cancels here. It'd be nice if something canceled, but nothing did. And you might say, oh man, that was exhausting. I'm so glad we finished this problem. We haven't finished the problem. We're trying to find the domain of f of g. So I said, to find the domain of f of g, we need to find the domain of the inside function, which we did. The domain of the inside function, we found that right here. Everything except for 2/3. We have to combine that. Gabe. We have to combine that with the domain of the final answer. So what's this second domain? What's the domain? Let's call it D2. Of this thing over here. You know, no, it's not like a horror movie. Not at all, Monet. You know why? Because in horror movies, they always split up like idiots. And here, crap, we're all watching from our homes. We are all split up like idiots. Well, we're together on chat at least, okay? So we're sticking together, we're working together, and we're gonna, all right, maybe you are right, Monet. Maybe this sounds like a horror movie. So how do we find the domain of this thing? Remember, it's a fraction. So someone tell me what the domain of this thing is, this final expression. Using the same way that we found the domain of this guy, because they're both rational expressions. All right, someone give it to me. Or at least say that you don't know. Give me something. Otherwise, I'm just going to scare the webcam and it'll be weird. So we don't want to cause a global disaster. To find the domain of a rational expression is all the things that we can plug in. It has to do with the denominator. Exactly, Gabe. What are all the things that we can plug in here? Well, we can plug in anything as long as it makes the denominator not 0. Same as we set up here. Okay? We need the denominator to not be 0. So what's the denominator? The denominator is 3 times 2 minus x. We need this not to be 0. Divide both sides by 3. 0 divided by 3 is still 0. And then we can add an x to both sides or subtract the 2. It's up to you. So x cannot be 2. And so now we found the two domains. Remember, to find the domain of f of g, first find the domain of the inside function, that was d1. And see what it has in common with the domain of the final function. So we need to combine both of these, d1 and d2, for our final answer. So we are right about to finish this problem. Our final answer is going to be the set of all x. Remember set builder notation, such that x is not equal to 2/3 and x is not equal to 2. X is not equal to 2/3 or 2. And this is our final answer. This is our beautiful domain. And we are done. We divided both sides by 3. So when you divided this side by 3, it goes away. When we divide this by 3, 0 divided by 3 is still 0. Good. Any other questions? That was a whopper of a problem. That was kind of fun. So remember, the big thing I want you to remember, just remember everything, okay? All right. That's my advice. We divided both sides of the equation by 3 right here. So that's where it went. Well, technically it's like an inequation. It's a non-equation. All right. Let's do another one, okay? So maybe you're still nervous about that one. Maybe you're starting to sweat. But if you're sweating, it's getting a little warm around Wyoming. If you're sweating, we're going to go take a jump into like a pool or a lake or something right here. And you'll cool down, no problem. Okay, let's do it again. Part B. Part A, we dealt with rational expressions. Remember, rational expressions, the denominator can't be 0. So to find the domain, we said, when is the denominator not equal to 0? Yeah, a Jello soap bath. In part B, we're going to talk about square roots. And remember, for square roots, we need the inside, the radicand, to be greater than or equal to 0. All right. All right, Delaney and Lexi are not sweating. That's perfect. Great to hear. You can be a shining example for the rest of the class. All right, so we got part B. Do the same thing for f of x equals the square root of x plus 2. And g of x equals the square root of 3 minus x. Okay. So we need to find the domain of the inside function and the domain of the final function and them together. It's kind of a disgusting sound effect, huh? You can make sound effects a lot more easier when I stream these lectures online than in class. Listen to this. Isn't that nice? You don't get that kind of quality in a classroom. Okay, so we need to find f of g. Okay. Wait, gross? Come on. So, let's find f of g. And remember, f of g is just f of g of x. We start with that inside function, and we work our way down. So what's the inside function? The inside function is g of x. G of x is the square root of 3 minus x. So since that's the case, we just plug it in for g. We replace the g of x with what it equals. Square root of 3 minus x. All right. Ding dong, ding dong, ding dong. The bells are tolling, okay? Because as soon as we do this, we say, okay, what's the inside function? What's the domain of the inside function? What's our d1? So just like before, when we look at the inside function, before we said, okay, denominator can't be 0, so x can't be 2/3. Well, that's what we're doing over here as well, but this is not a rational expression. We don't care if anything's 0 here because we're not dividing by 0. That was the issue before for rational expressions. We didn't want to divide by 0. There's no division at all here. For square roots, though, we have a separate requirement. If we want things to be real, and I promise you, none of you, or probably almost none of you, want to worry about complex valued functions. We're going to stay real right now. All right. So for this to happen, we need the inside of the square root or the radicand to be greater than or equal to 0. So what's the radicand here? Radicand is what's inside the square root. So we need 3 minus x to be greater than or equal to 0. So you need to solve this inequality. Wait a minute, solve the inequality. Oh, we've done that before. What a coincidence. Look, what a coincidence that so many of the things we're doing in 1400 are topics that we covered in 930. Wow, what a fortunate coincidence. Okay? This is why it's really important for you to have succeeded in 930. Otherwise, 1400 gets way harder. And again, I try to make my 9:30 class pretty difficult so that if you do pass, and literally all of you students have passed, you should be ready for this class. All right? Not to say it's not going to be hard. It'll still be hard. But it'll be hard but possible. Okay? It's like the difference between eating stale bread. That's hard, but you can still eat stale bread. And eating a concrete block. You can't eat a concrete block. Okay? So I have taken the concrete block and turned it into stale bread. So you're all eating stale bread right now. Okay? So we solve this inequality. We subtract 3 from both sides. Negative x is greater than or equal to negative 3. Divide both sides by negative 1. Okay? We divide by a negative, switch the direction of the inequality. All right. So that's our first requirement. And now we need to finish simplifying to find D2. Just like we did on the first problem, right? We started evaluating f of g. We found D1, our first domain, was the inside function. And then we fully simplified to find D2 by looking at this final thing. That's what we're doing here as well. So we need to plug in this inside function into our f. And y'all are going to hate me for this. I already know. These problems are doozies. Remember yesterday I said that today's material is going to be the worst part of the section? I wasn't lying to you. This problem's a doozy. Look at what happens. We need to plug this inside into f. Well, what is f? F says, the function f says, you take the square root of your input plus 2. So f is the square root of your input plus 2. But here our input is x, so there's just an x here. Here our input is the square root of 3 minus x. Okay? So the thing, we're plugging in the square root of 3 minus x into this function. The x is getting replaced by this input. So we don't have the square root of x plus 2 anymore here, because x is getting replaced by this whole thing. So we got a square root inside of a square root. Whoa! All right? And that can't be simplified. There's no simplifying to be done here. Excuse me. That's maybe the appropriate response. Okay. So this is as fully simplified as it gets. So we need to find D2. We need to look at the domain of this. All right. What is it called? Like the Mariana Trench or something? Something like that. The ocean's pretty deep. Okay. So for our domain 2, our D2, we already found our D1. We need to look at the domain of this final function. So we still have the same restriction from before. X has to be less than or equal to 3 because of this guy. Now we have to look at this whole thing. Can this whole thing ever be negative? And the answer is no. And this is kind of complicated. I recognize that, okay? Kind of. This is complicated. I recognize that, okay? But to look at this, we need the inside, we need the radicand to be, right? What do we need? We need the radicand, which is the square root of 3 minus x, plus 2 to be greater than or equal to 0. And this is where range comes in to save the day. Range is like a superhero. If you're sinking, Range put on a superhero cape and he went down into the depths of the ocean to pull you back up, okay? Because Range can fly. All right. What is the range of a square root function? You remember square root functions, right? They look like this. They kind of look like half of sideways parabolas. Range was the y values, the vi values. Ranges of I values. Right? What is the range of this? It was 0 to infinity. So the range is never negative. So if this thing, range is the output, if this thing is always greater than or equal to 0, then isn't this always true? We have something greater than or equal to 0 plus 2. Well, that's, of course, if you add a 2 to something that's positive, it's still going to be positive. Always true. Happy face. Wow. How about that? No, not Bible thump. Happy face. Okay, hold on. I got to fix this. There we go. So we're just going to combine these two things and get our answer. So to get our answer, we need to combine D1 and D2. D1 says, okay, x has to be less than or equal to 3. D2 says, you know what? I'm not going to be a restriction. You do whatever you want. So the only restriction we have is this one. So our domain is going to be the set of all x such that x is less than or equal to 3. And that's it. Okay? So, yeah, that's that. There's going to be some of these on the homework. And you know what you're going to do? You're going to look at them, because they'll be due on Thursday. You're going to look at them and say, this is difficult. Why don't I ask Jason a question about this? So you're going to go on the Discord. You're going to ask me a question. I'm going to answer your question, and you're going to feel better. Okay? But if you never ask questions, you're just always going to be confused. Okay? So you need to do the homework. You can't just learn this by watching it. I'm trying to give you the material you need to like put in the work and figure it out, because you're not going to just figure all this stuff out while listening to lectures. You have to learn math by doing it. Okay? So use this as a springboard for your homework assignments and just ask questions. Work with others. Talk to other people, okay? It's hard, right? And this class is going to be hard. Okay? Crying is okay. But when you're done crying, you can start the homework assignment and ask me questions. Is that rude? That sounds a little rude. I have something for all of you, okay? If you're feeling like this is rough, I got something for you. Okay? First off, upside down math. Appreciate that at least you don't have to do upside down math, right? That would be worse. Second off, I'd like to remind you all that there are still cute little cats in the world, okay? All right. So it's not that bad. All right, let's finish the section. Okay? But really, really legitimately, you do have to do a bunch of homework problems and you do have to ask me questions. Otherwise, this class is going to be much worse than it has to be. I mean, I did think your cat was kind of scary, but that's not an insult. I'm scared by a lot of things. Some people are scared of math. Can you imagine that being? Maybe some of you could imagine that. Let's finish the section. Okay? Don't worry. The last problem is not as bad. The last problem is like a cool down. It's like we just ran a marathon and now it's like, okay, walk around the block. You're going to be tired. You just ran a marathon, but you can walk around the block. Write h of x as the composition of two functions. F of g. Okay? So, part A. h of x equals the square root of 5 minus x squared. So, right, we want to write it as f of g. And remember, right, recall f of g of x is f of g. So g is our inside function and f is our outside function. So all you need to do here is identify what's your inside function and what's your outside function. And there's multiple answers. So just try, sorry for laughing, just try to identify an inside function. So take right now, what would be an inside function? What do you think an inside function is? We haven't done one of these, but do you have a guess of something that could make sense as an inside function? If so, write it in the chat. Okay. I think you've got this. What could be an inside function here for part A? We're trying to identify an inside function and an outside function so that we can write it as a composition. Now, any guesses? Someone give me a guess, even if it's a terrible guess. Bella says help. Well, right, 5 minus x squared is on the inside of the radical. Technically, 5 almost works, actually. 0 is not quite it. We're just going to choose the function that's on the inside of the square root. It's probably the easiest choice. The square root is close, Delaney, yeah. The square root, actually, we're going to use as our outside function. The inside function, let's just choose as 5 minus x squared, just what's on the inside of the square root. And then the outside function is what's being done to that inside function. So the outside function is going to be the square root of x. Okay. So that if you plug in your inside to your outside, you should get h. So notice, if we plug this into, right, if we plug this into our outside function, we do get the square root of 5 minus x squared, which is exactly what we wanted. Okay, so that's how you sort of approach these. Let's do another one. H of x equals 4 divided by 3 minus the square root of 4 plus x squared. There's a lot of answers for this one. Okay. But someone give me an inside function. And again, there's a lot of options. The outside function's usually harder. And you can follow the same logic that we did in part A, or you can extend the logic and choose a different inside function. We'll do 4 plus x squared, but yeah, that'll work. So if you want to use your 4 plus x squared as your inside function, what does your outside function have to be? Your outside function has to be something so that when you plug the inside into the outside, you get h. Yeah, good, Gabe. It's going to deal with the square root of x, but we also need this fraction. So it'll have a square root in it. It's going to be 4 divided by 3 minus the square root of x. Yeah, good, Stella. Yeah, nice. Because notice what happens, right? If we plug our inside into our outside, we get 4 divided by 3 minus the square root of 4 plus x squared. All right? Which is exactly what we wanted. So this is going to be our answer for this. You could have chosen other things as well, right? Another choice of inside function could have been the whole denominator if you wanted. 3 minus the square root of 4 plus x squared. This could have worked for an inside function as well. And then if this was our inside function, then our outside function would be 4 over x. Because again, when you plug the inside into the outside, you get 4 divided by 3 minus that square root, which is what we wanted. So there's a lot of answers for this. The important thing is if you do something like example 8, just check your answer and plug your outside function into your inside function and make sure that you get the same thing. Questions on this section? We're going to start the next section after this. This is the last section that'll be on your exam though, but again, we have a ton of material and really only 6 or 7 weeks to do it in because of the weird things that have happened with this semester. And again, I don't expect that you're going to be able to just learn everything during the lecture. You have to look at the problems and you have to ask me questions. You have to work with some other people, okay? It's going to be hard, but if you put in the time and you struggle and look for help and ask for help, you're going to get it. I literally, I say this with full confidence. I would not have passed any of you if I did not think you were ready for this material. I think literally all of you are going to pass this class as long as you have the time that you need to dedicate it, okay? And I don't say that about all my 1,400 classes, okay? Well, if Lane's tired of you, which I doubt, ask me, okay? That's what I'm here for. Let's start the next section. So, this section is really cool, okay? So, you might not like this section, but I like this section, so whatever. This section is this next section is transformations of functions. Okay, first off, this is a really good section to do an online class because I'm going to be showing you things on the computer. Second off, this might be the single most useful section in this whole class, okay? As far as how often it gets used in like every area of mathematics ever, okay? So we're going to talk about things to do to functions. So what we're going to do is we're just going to start by doing a little bit of review, okay? So what we're going to need is I'm going to need you, if you're taking notes, as would be a good idea to be taking notes. If you're taking notes, put them to the side real quick. Get your computer in front of you and get ready to type, okay? I need answers in chat. We're going to do a little review quiz, okay? Before we get into compositions of functions, all right? So what's going to happen is I'm going to put a function and you are going to tell me what kind of function it is. Remember the toolkit functions that we talked about earlier. Okay? We'll start with one that I think you know. We'll start with one I think you know. Okay? What is the equation of this function? I know somebody knows this. Yeah, x squared. Good. Uh-huh. Let's do another one. What about this one? We've talked about this one literally today. So that's your hint. Because we're going to be using these toolkit functions today in this section. It's really important to remember them. This one over here looks kind of like an x squared, but it's sideways and only half of it. This is going to be the square root of x. Yep, good. So we got more of these. Remember, this one was x cubed. And then there's like a sideways version of it. Let's plot them both at the same time, right? This yellow, orangish, brownish, gross looking one is the cubed root of x. Interesting geometric relation, by the way, between these two, don't you think? They make this sort of symmetric looking pattern. Wait a minute. It's like if you reflect the blue one around the pink, you get the brown one. Interesting. We're going to be talking about that in 3.7. These are inverse functions of each other. Okay? All right. Let's look at some more toolkit functions that we're going to talk about. The reciprocal function, 1 over x. We're going to use that. The squared reciprocal function, 1 over x squared. We're going to use this. By the end of this section, you need to be familiar with all of these. Okay? No pressure. We're going to spend a lot of time on this section, though. It's long. And this will not be on your exam on Thursday. So that's silver lining. Okay? And then there are some simpler functions that you should be aware of, right? The identity line function, y equals x, just a diagonal line, right? Constant functions, y equals 5, it's just a flat line, or y equals 2, you could put it wherever you want. It's always just a flat line. So very important to be familiar with these toolkit functions. We're going to use these a lot. So we're going to start today by talking about transformations. And what I mean by a transformation is, what if we have a function and we do stuff to that function? So all the transformations we're going to talk about are like, for example, what if we multiply the function by a 2? We get y equals 2x squared up here. What happened? It kind of got squished a little bit, right? That's a function transformation that we're going to talk about in this section. What if we add a 2? Oh, it got moved up, right? This is a function transformation that we're going to talk about. In fact, let's actually do these right here. We'll keep the blue one as the basic function, the toolkit function. And the white function is the transformed function. So if we add a 2, it just moves all the points up 2. This white graph is just the blue graph moved up 2. All right? If we subtracted 2, you know what would happen? It just moved down 2. Okay? There's only one section, Bella. You could just not even show up for the quiz on this section and still pass this class. Remember, you still get 4 dropped, 3 dropped. I don't remember how many quizzes. I think you only get 3 dropped now because we have fewer quizzes in this class. You'll be okay. So we just subtract 2. All right? These are all function transformations. What if we put a negative in front of over here? If we put a negative, it just flips it upside down. All function transformations. This is all the stuff that we're going to talk about then. And there's even more fun stuff we can do. What if instead of putting a 2 on the outside, we put it on the inside? Whoa! Now it doesn't go up. It goes to the left. If we subtract a 2, it goes to the right. Wow. All of these function transformations. So that is just, obviously, you're not going to know all of the stuff I just talked about, but that's kind of what this section's about. That's what's going on in this section. And we're going to break all of these things down into the tiniest little baby steps so that by the end of this section, you will be able to do that yourself. And by the end of the section, you're going to be combining function transformations left and right. You're going to do all sorts of things of the graph all at once. You will be a function transformation ace. All right? So that's what we're doing here. Okay, so let's get started. We'll start with the easier ones, simpler ones. Not easy, just easier. Okay, so what I'm going to need you to do is make a table. Okay? with 3 columns. The first column is what transformation is. Second column is going to be the definition. And the third column is going to be an example. All right, make it take up the whole thing. And we are going to fill this with, don't freak out, with 10 things. Okay? So if you're using lined paper, you need to leave room for 10 lines, at least. Okay? But don't worry, we're just doing one at a time. We're going to do one, then we're going to do some examples, then we're going to do another and do some examples so you can see why we're going to spend a long time on this section. All right? And again, that's kind of why we're not reviewing today, because there's really not time. I'd rather not be rushed in this section. It's worth it to talk about for a while. So let's get started on our 10 lines. Vertical transformation. Okay? Vertical shift. Up. C. What that looks like is you have a function and you add a number at the very end. That's going to move the whole graph up C units. So for an example, we can use something we just talked about. If you have a parabola and you just add 2 to the end, it moves it up 2. And this is kind of like, these are going to go kind of fast, because if adding C goes up, you already know what this is going to be, right? You already know what to expect if you subtract C, right? If we had y equals x squared minus 2, you know what would happen. If adding 2 moves it up, well, then subtracting 2 is just going to move it down, okay? So vertical shift down C units is going to be our second one. We are already 2 out of 10. So again, let's just really spend some time and look at this. If you add a number to the very end of the function, it moves it up or down. Okay? So we've got something over here. Let's go back to a function. If we just add something, it moves the whole thing up. Let's just stick with the blue graph. Right? Moves it up. If we subtract it, it moves it down. Let's look at other toolkit functions. If we add something to a square root function at the very end, it just moves the whole thing up. If we subtract, it moves the whole thing down. Another toolkit function. We add something to the end, it moves everything up. If we subtract it, it moves everything down. So these are all examples of things. Look on the left. Look at the formula on the left to see what you can kind of look like. Added something, moves the whole graph up. Subtracted on the outside at the very end, moves the whole thing down. And that's how we're going to start this section. This is essentially 1/5 of the section already. Okay? And we are going to spend a ton of time with this. We're not even going to finish this in tomorrow's class. Almost assuredly, we're not going to finish in tomorrow's class. It's a long section. All right? And remember, exam is on Thursday, and we will have Easter holiday on Friday. So you take your exam on Thursday during class. That means no class on Thursday, just the exam. And then no class on Friday either. So you're going to get a bit of a break, which you may or may not need a bit of a break. You may not want a break. You may say, wow, I'm so on fire for mathematics. I don't want a break at all. I just want to do more and more math. Well, sorry. You can work ahead if you want. All right. But most of you are going to get that break. Okay. So some other things I want to talk about real quickly before I let you get to your quiz. So Thursday's the exam. You're going to take a quiz right after this. Okay. Quiz is going to start soon. And tomorrow we'll finish the section. Thursday will be the exam. Friday is holiday. And we'll probably finish the section next week, Monday. All right. So remember, it's going to be tough. Go through the homework problems. Go through the exam review. Ask me questions, please. All right. You're not alone in this. All right. Your classmates are probably willing to work with you. And I'm definitely willing to work with you. It's literally my job to help you succeed. Okay, not even if I didn't care about you at all, which I do. I care about my students. Even if I didn't care about my students, it's literally my job to help you guys succeed. So I'm here for you. Don't feel like you're alone. Don't feel that like you're isolated, even though, you know, physically we're all isolated right now. But please don't hesitate to reach out. All right. Good luck on your quiz. Go ahead and get started with it now. And I'll see you tomorrow.